This video looks at the step response behaviours of a state space model. Previous videos then focused on solutions for models of the form x dot equals ax and showed that these could be written as x of t equals 5t x of 0. And 5t could be solved in a number of different ways. You could write e to the at, you could use an eigenvalue eigenvector decomposition and write w e to the lambda tv, or you could use Laplace and write the inverse Laplace of si minus a inverse. This video is going to consider what happens when we add an input to a state space system. So now we've got a model of this form, x dot equals ax plus bu, and the generic solution has still got the dependence on initial conditions, this 5t x of 0, but we've got an additional term, h of tu, where h of t is the step response because we're assuming here that u is a constant. And this video is looking at how do we calculate h of t. There are two obvious possibilities for calculating h: to use Laplace transforms or to use a convolution integral. It was mentioned in the first video in this section that using Laplace transforms is rather cumbersome and difficult and tedious, etc., etc. So I would recommend that if you want to use the Laplace method, use a numerical tool to get numerical answers, a software tool. Don't do it on pen and paper because you'll get rather bored. Illustration here. It's obvious that if u of t is a constant and you ignore initial conditions, so there's our model, then you can solve for the Laplace transform of the state x by writing x of s equals si minus a inverse times b times u over s. And the key point here is that u over s is the Laplace transform of the step input. I can therefore solve for the step response by doing the inverse Laplace of this transform here, si minus a inverse b over s. Now it's probably obvious that this is likely to be tedious and difficult if you want to do it on pen and paper, but it's a solution you can use if you want to. What about convolution integral methods then? If you take, for example, a single input, single output system with an impulse response e to the at, then a convolution integral is a well-known way of finding the response for an arbitrary input. So here's the convolution integral. I've taken a model, x dot equals ax plus bu, and it's got an impulse response e to the at. Now I can write the overall solution, x of t, as e to the at x of 0, and then I have this convolution term here, the integral between 0 and t, e to the a t minus tau b, and I should have written in there u of tau, but d tau. Now we're assuming u is constant. An equivalent solution for matrices is going to follow exactly the same form of pattern. The only difference is we've got e to the at, where a is a matrix. So you'll see we've got e to the at x of 0, and the integral part takes exactly the same form, apart from we have matrices rather than scalars. So e to the at minus tau, capital B, u, d tau. So this is a generic solution for how x of t depends on the initial condition x of 0 and depends upon the input u. Now this integral is relatively easy to perform. So first we remember from the previous video that the derivative of e to the at is a e to the at, and we're going to use that result. Here's the integral that we need to do. The integral between 0 and t, e to the a t minus tau bu d tau, and doing the integration you'll notice we get a minus a to the minus 1 out the front, and then an e to the a t minus tau bu between the limits 0 and t. If I substitute in those limits, you're going to get these two terms, minus a inverse e to the a times 0 bu, and then a double minus a inverse e to the a t bu. And finally, solving for that, e to the a0 is the identity, so you'll notice you end up with this expression here, that the step response h of t is given by a inverse e to the at minus I times b. So we have an explicit expression for the step response. We can use superposition, so the step response from non-zero initial conditions is given by this sort of form. Phi of t, which was covered in the first two videos, times x of 0, plus h of t times u, and h of t has been defined in this video. And those are the definitions. So phi of t is e to the at, and h of t is a inverse times phi of t minus I times b. If you had an output equation y equals cx, then you could very quickly write that y of t equals c times phi x of 0 and c times h times u.